Hello, everyone. Thank you so much for joining us today. It's really fun to see where everybody is joining us from. So my inclination was always to say good afternoon because that's where I am. But I think good morning and good evening are also completely valid for all of you out there. My name is Summer Ash. I am the STEAM Education Manager for NRAO, and I am based in Socorro, New Mexico, which is where our lovely VLA also is. And before we get started today, I would just like to introduce my team members that are joining us today. So Faith, if you could stop screen sharing for just a second, turn on your video, and Tyler, if you could turn on your video and join us. Thanks. Would you like to introduce yourself, Faith?
Hey everyone, so I'm Faith Vowler. I am the education specialist here at NRAO and the VLA. I'm also based in Socorro. In fact, Summer and I share an office here. And so this is where a lot of our staff members work, including some like us who work both at the VLA and here in town in our office building.
Tyler.
Hi everyone, I'm Tyler Cohen. I am a graduate student here in Socorro and also a part-time VLA tour guide.
Thanks, guys. So today's tour is focusing on mapping the radio sky and VLA Sky Surveys. I am going to hand it off to Faith, who is going to give you an introduction to the VLA and to some of the sky surveys that we have done and are currently doing. And then I will come back again to have some conversations with some of our special guest experts today. So take it away, Faith. Faith, you're muted.
Oh, sorry, everybody. So great. So, hey, everyone. So first, we're just going to do a little bit of housekeeping here real quick to before we get started about for how Zoom will work. So this webinar will be about an hour. And if you have any questions for us throughout the presentation, please use the Zoom Q&A feature that, as you can see, is right here on the screen, and that will just help us find the questions more easily. There's going to be a dedicated time for questions later on in the presentation, and some of them we will answer for you in the Q&A feature, and others we will ask out loud to our panelists. The Zoom chat feature is where you can talk to other visitors and audience members. And also if there are any technical difficulties, you can let us know about those there too. And please make sure that your messages are set to go to all panelists and attendees. That's also helpful for if there are technical difficulties, you'll be able to see other people's messages and more easily figure out if it's something on your end or on our end. And during the tour today, Tyler is going to be posting links to some of the websites that we'll be talking about in the chat, but we'll also, when we send a post webinar email to you, the links will be included there as well. And so we will try to answer as many questions as we can, but we aren't always able to answer all of them. So if you have a question either that we're not able to answer, or you think of a question later that you'd like to ask, you can go to our Ask an Astronomer feature here on our webpage. And you can search through the archives of questions that have been asked before and see if your question or a similar one is already there. And then if it's not, you can submit your own question. And usually the answers to those are posted within a few days. And so we're also going to have 3 different guest speakers with us today to talk more about their work with the radio surveys that we're going to be talking about. So that will include James Corden, an astronomer emeritus, Amy Kimball, an assistant scientist and the head of operations for VLASS, and Sergio Garza, who's a scientific data analyst. And so to start things off here, so the VLA, the Very Large Array, is owned and operated by the National Radio Astronomy Observatory, or NRAO. And NRAO was founded in the 1950s with the goal of building and operating observatories to study radio light that comes to us from space. So if you probably, when you think of a telescope, often think of looking through an eyepiece up at objects in the sky. That's when you're studying visible or optical light, the kind that your eyes are able to see. But radio light is a type of invisible light, so our eyes aren't capable of seeing it, but the telescopes and observatories that we build at NRAO specialize in observing that type of light. And we're funded by the National Science Foundation, NSF. And so that means that a very small portion of your tax dollars does go towards paying for the work that we do. But to us, it's a very significant portion of your tax dollars. That's why we think it's very important to be able to share the work that we do with you at these observatories. And so of these, so we operate 3 different major telescopes, and of these 3, the one that we'll be talking about today in detail is the Very Large Array. And the VLA consists of 27 antennas. We technically have 28, but we use 27 at any given time in our observations. And each of these dishes is about 90 feet or 10 stories tall. And the dishes are 82 feet or 25 meters wide in diameter. And we're at a latitude of 34 degrees north. And so from here, the VLA is able to see about 72% of the objects in our sky, which is pretty good. That just means that the remaining 28% are too low, too far south for us to be able to see. And so the VLA was built on the plains of San Agustin in an ancient lake bed out in the desert in New Mexico. And we started building it in the 1970s. And we completed it and dedicated it on October 10th, 1980. And we chose this particular location because it's what we call high and dry. And so it's at about 7,000 feet or about 2,150 meters above sea level. And so when light is coming to us from space, the air in our atmosphere tends to bend or distort that light, which is an issue that we have when we build telescopes here on Earth in general, not just radio observatories, but any type of telescope. And so by building it at a higher elevation where the air is a little bit thinner, we can lessen that problem. And you also don't want to build big observatories in places that have a lot of humidity, because moisture in the air is another issue that tends to distort that light coming to us from space. And so when we build it in a dry location, like in the desert, we're lessening that problem as well. And as you can see in the picture here, where the VLA is also surrounded by mountains in many directions. And so that acts like a natural shielding for us. As you can probably imagine, large cities like Albuquerque, Santa Fe, Las Cruces, and even smaller cities have a lot of Wi-Fi and cell phones and devices that can interfere with our radio telescopes. And so these mountains act as sort of a shielding from those large cities that could cause interference for the VLA. And so on site at the VLA, like I said, we have 28 total dishes. At any given time, we tend to have one over at our antenna barn, which is undergoing maintenance. And we operate the VLA from our control building that's located on site. So we have VLA operators where that's their job to go out to the site and operate the VLA during its scientific observations. And so the VLA is arranged in a Y shape, as you can see here in these pictures, made up of 3 different arms. You have the west and the east arms that are 13 miles each of double railroad tracks, and the north arm, which is 11 miles of railroad tracks. And that one's just a little bit shorter because way up at the end of the north arm, there's a ravine up there that would have been really expensive to build a bridge over. So rather than doing that, we just shortened that arm a little bit. And on these sets of railroad tracks, there are a total of 72 different stations that can have VLA antennas on them. So it would be great if we had 72 antennas and could have one at each station. But as you can probably imagine, these antennas are really expensive to build. So we built 28 of them because that's what we could afford to build. So and what we do instead is with the 27 antennas that we're using at any given time, we'll move them on these different stations to be closer together or further apart, which gives us the effect of zooming out or zooming in when we look at the sky. So we have 4 major different configurations that we'll arrange these antennas in. We were feeling quite creative the day that we named them, so we called them A, B, C, and D. And in the A configuration, when the antennas are a long way away from each other, if you were to draw a circle around the outer edges of the antennas, that circle would have a diameter of 22 miles or 36 kilometers. And then you have the B configuration, which is 7 miles or 11 kilometers in diameter. The C configuration, 2 miles or about 3.5 kilometers in diameter. And then the D configuration, when the antennas are darn close together, and that has a diameter of about 0.6 miles or 1 kilometer. And so this is a map that shows just how big of a difference there is between the different size configurations. So the small white circle that you see here in the middle is the D configuration. Then you have C right here, and you have the B configuration here, and the A configuration is the big white circle around the edges. And when we move between these configurations, we go from smallest to largest, so backwards in alphabetical order, D to C to B to A, and then back down to D. And so the differences between what kinds of stuff you can see if you're using the different configurations, the smaller ones like C and especially D allow you to see, that's when you're the most zoomed out. So you can see larger structures in the sky, such as this object here, Hercules A. You can see the large puffs of the puffy clouds that in these more tightly packed configurations. And then in the ones that are further apart, like B and especially A, this is when you're the most zoomed in. So you can see the highest resolution, the finest detail. As you can see in these pictures, it allows us to see what's happening in the middle of this object more easily. And so many times astronomers will want to use all 4 configurations to look at an object and combine the images of each one, and that'll give them the best idea of what they're looking at. But it also just kind of depends on what you're trying to observe. Sometimes, depending on what the astronomer wants, they might only need the larger structures that you see in the C and D configurations, or they might only want those really fine details from A and B. And so when we move these antennas from these different configurations, we use our VLA transporters. There are 2 of them, and they were uniquely made to carry the VLA antennas. So they're the only 2 like them in the world. Our antennas weigh 230 tons or 460,000 pounds. So naturally, we did have to specially make these machines to be able to carry those. And each station is fully equipped. Each of the 72 stations is fully equipped with all the electronics that the antennas need to run. So when we're moving them, we don't have to bring along a lot of electronic cables or anything like that. We just take them to the new stations, pick them up, carry them, put them down, and then plug them in. And after we get them up and running from there, it doesn't take too long before we're able to start using them again in their new locations. And these transporters move quite slowly. Their maximum speed is only 5 miles per hour, or about 8 kilometers per hour. And when we're actually carrying an antenna on them, they only move at about 1 to 2 miles per hour, or about 1.5 to 3 kilometers per hour. For safety purposes, naturally, we don't want to have a transporter go zooming down the tracks and have an antenna fall off. That would be really, really bad. And also, if it's really windy, like over 20 miles per hour or 32 kilometer per hour wind speeds, we don't move antennas at all during that, because again, we don't want to risk them potentially tipping over. And at the VLA, we have what's called the 3 antenna rule, where out of the 27 antennas on the array, so not counting the 28th one in the barn, out of those 27, we can have up to 3 that we're not using at any given time. Maybe 2 of them are being carried by the 2 transporters. Maybe there's one that's having a bad day, and so we're not using it. As long as we have 24 or more of them up and running, we can still get enough data to keep our scientists happy. But of course, the more we can have running, the best case scenario it'll be. And so we have, as you can see here, these show a more close-up view of the receivers that we have on these antennas. And so these are what actually get the data. And so we have different receivers for different wavelengths or frequencies of light that we want to look at. So the VLA is able to look at frequencies of between 1 and 50 gigahertz regularly. We can go a little higher, a little lower, but that's our typical range that we operate within. And so 1 gigahertz would be a 30 centimeter long wavelength. 50 gigahertz would be 6 millimeters. And so we have 10 total receivers here in the middle of the dishes, but 8 main ones that we use. And so what happens is the light hits the dish and then it bounces up to the subreflector here at the top. And depending on which wavelengths or frequencies the scientists want to use, the subreflector will bounce the light into one of these receivers. So now to move on talking about sky surveys. That was just a background about the VLA and how that works. So we have a few different reasons to do sky surveys. So it allows us to make a map of the sky in a systematic format. We can discover new objects by doing this, which is always something that is really exciting in astronomy. We can do demographic studies of what we're looking at, and we create catalogs out of the data that we find that can act as sources of data for the community to use, just in general. And so early surveys that we did with the VLA, we had the first ones were done in the early to mid 1990s. And we had the NRAO/VLA Sky Survey, or NVSS as we called it, and the Faint Images of Radio Sky at 20 Centimeters survey first. So that one's, yeah, both of those are a little bit long mouthfuls. So you can see why we shortened those there. And both surveys were done at the same frequency of 1.4 gigahertz, which is 20 centimeter wavelength. And but the 2 surveys did differ in size and resolution, so like how zoomed in they were. So NVSS used the D configuration, so the most zoomed out one, and observed the full sky over the VLA above 40 degrees declination, which is about 82% of the total sky. And first was much smaller. And so it focused on a smaller area of the sky, only covered about 22% of it. And it used the B configuration, so the second largest or second most zoomed in. And so NVSS, since it was made with the D configuration, was more sensitive to those diffuse or extended sources, the larger structures, but the positions were less accurate, whereas FIRST was capable of detecting fainter sources because it was done in the B configuration and had more accurate positions as a result. And so these images here show how the resolution of the two different catalogs differ. So these are called contour plots, and they show the intensity of the radio signals as seen by NVSS on the left and FIRST on the right. And you can think of a contour plot as like a topographical map, so similar to maps of mountains here on Earth. But here the contours represent the magnitude of radio signals instead of altitude or height. So in this case, FIRST was able to resolve an NVSS source into 4 separate radio sources. So that one picture of NVSS makes it a lot harder to tell that those are actually different objects. And this example shows how FIRST was, oh yeah, so this is like another example of going into more detail and observing more structure in the form of the core of a radio galaxy with active jets. So it's a lot harder to tell that that is a galaxy with active jets in NVSS. It sort of just shows up. We can definitely see it. It's just looks like more of one big blob when we look at it in NVSS. And so then the current survey that we're working on is the VLA Sky Survey, or VLASS. And so one thing to know too about the VLA is that starting in the early 2000s, we began to upgrade it. So as you all probably know, technology gets better and better over time. And so that means that if you built something at a certain time, it will start to fall behind more and more technologically unless you make improvements to it. And so NVSS and FIRST were taken in the 90s before we did those upgrades. VLASS is a survey that we started doing recently. So after these upgrades were completed in 2012. And so the VLASS involves scanning and mapping the entire sky that the VLA can see a total of 3 times over the course of about 8 years. So this project, we started doing it in September 2017. So it'll be complete in 2025. And we're observing millions of different objects in the sky. And like FIRST, VLASS uses the B configuration, and it also uses a hybrid where the north arm is in the A configuration, so that full 11-mile track there, and the west and east arms remain in the B configuration. So that that's the BNA that's listed right here. And so normally we switch between the VLA configurations every 4 months. So it's a 16-month cycle. And before we started doing VLASS, we stayed in each configuration for about an equal amount of time. But now, because we're using the B configuration to do this survey, we want to make sure that we have enough time to do VLASS observations, but also still, if there are other scientists and astronomers who want to use the B configuration for other projects, we want them to have the chance to do so. So currently we're extending our B configurations to something more like five or so months, and we're shortening the A, C, and D configurations to more like 3 months each. And before we move from the B to the A configurations, when we move into that hybrid, that BNA configuration, we stay there for about 2 or 3 weeks. And while we're in the BNA configuration, we use that solely for VLASS observation. So that's just a few straight weeks of being able to work on VLASS. And this is a totally public project. So the data from VLASS, once it's been properly compiled and put together, is completely available on this website that you see here for the public to use. And so by the numbers, like I said, it began in September 2017. And it's the highest spatial resolution all sky radio survey ever undertaken. And so again, 82% of the all sky. So that's what it has in common. That's one thing it has in common with the NVSS, that it looks at the whole sky that we are able to see. It uses a frequency of 3 gigahertz for the most part, varies between 2 to 4 gigahertz in areas that are less affected by radio frequency interference, or RFI. And again, we use the B configuration, so that gives us an angular resolution of 2.5 arc seconds. And the cadence is 3 epochs are separated by 32 months. So that's what, like I said, we scan the entire sky a total of 3 times as part of this project. And we use 920 hours per each time we're in the B configuration to do VLASS observations. And so that adds up to a total of 5,520 hours over those 7 years that we're conducting this survey. And so earlier we showed you a comparison of NVSS and FIRST. And so now we've added a VLASS to illustrate its superior resolving power to the other two. So if you recall, NVSS has a resolution of 45 arc seconds and FIRST was 5 arc seconds. But now with VLASS, we can get down to 2.5 arc seconds. So half the resolution is even about twice that of FIRST. So now we're going to hear more about these surveys and their importance. And so I'll hand it over to Summer, who can introduce our guest speakers.
Thanks so much, Faith. That was a great introduction. So Jim, if you could turn your camera and microphone on now. Thank you. Yeah, so Jim, you have a history with NVSS, but that also means that you've been at NRAO for quite a long time. How long have you been here, or have you been with us?
Well, I started in 1972.
Oh my goodness.
Long before the VLA was built. And even then I was interested in doing all sky surveys, but I had to use single dish telescopes in Green Bank at the time. That was all that was available. And you may have heard of me. One of my most notorious moments was in 1988, I was using the 300-foot telescope to make a sky survey, and the telescope fell down basically from old age.
Not from all of that observing you were making it do.
Probably not, although the observing was certainly making it work.
Yeah, so you kind of answered my question. I was curious as to what the status of radio sky surveys was before NVSS and FIRST. So were most of them single dish surveys, essentially?
Most of them were. Certainly the all sky surveys were. Surveys were the first things that were done in radio astronomy when radio astronomy started in the 1930s, because nobody knew what was up there in the radio sky. And a radio telescope, even a single dish, can only look at a limited portion of the sky at once, so that you might want to observe something that you knew already, like the Andromeda galaxy. But if you only did that, you'd miss everything else, and there was a lot to be discovered. So it was quickly realized that all sky surveys made sense to explore the radio sky for further observations that followed up the discoveries.
And how did NVSS come about in the first place? How long did it take to sort of come up with the plan for it and then eventually enact it?
Well, the idea is fairly straightforward, to use an array of telescopes instead of a single dish to make a sky survey, because as you pointed out, the resolving power, the ability to see details improves if you have a larger telescope or an array that's spread out over a larger distance. So the idea was there in the air, but it wasn't technically practical until 1993, because at that time the VLA upgraded the 1.4 gigahertz receivers to the point that they were sufficiently sensitive to do this. Now, another factor was computing limitations. Normally, in the past, the arrays like the VLA would be used to observe a single source all day long. And reducing that data was enough to keep the computers very busy. And that there was more pressure on the computers really than on the telescope itself. But it finally became practical to just make a snapshot observation at each point in the sky and add up all those snapshots. So, for example, the VLA at 1.4 gigahertz can see at any one time a region of sky about a half a degree across, which is about the size of the full moon.
Right.
And say, how many different directions do I have to point to cover the whole sky visible to the VLA with that field of view? And the answer is 200,000. So for the NVSS, we observed 200,000 different positions on the sky, each for only 30 seconds of time.
Oh, wow. I didn't realize that.
What that meant is, of course, we had to make 200,000 maps. And it wasn't that easy then because the computers were so slow. So I can remember being very pleased when the director of the NRAO gave me my own personal Sun workstation with a 0.001 gigahertz processor in order to reduce these data. So that was one of the reasons why it took a while to do surveys like the NVSS.
That's incredible. I didn't realize it was such a short exposure time, or so to speak. That's the analogy for optical. But and in those all of those different pointings, it's around 101.8 billion sources that were detected.
So 1.8 million sources were ultimately detected.
Yeah. And the entire survey was also then made public, right?
It was public from the beginning, and we had the policy that the astronomers who were making the survey wouldn't use the data for their own science until the data had been posted on the web, so that everybody had an equal shot at exploiting the data.
That's really great. So what are some of or are there some exciting highlights of science that came out of NVSS?
Well, the main virtue of the NVSS is actually its low resolution. That is, when you go to the deconfiguration, you don't get to see as much detail, but you end up with much higher sensitivity to diffuse objects. And a lot of astronomical sources are diffuse, and if you don't see the diffuse sources, you've just plain missed them. My attitude was always, the purpose of a survey is to find sources, and you should design the survey so it finds as sources as possible and doesn't miss any. For example, spiral galaxies like our own are diffuse radio sources. And if you want to see radio emission from all of the spiral galaxies in the universe, you had to use the deconfiguration. And surveys in the B configuration, like FIRST or VLASS, cannot see most of those sources. Another feature of the NVSS was that it was designed to be extremely uniform and accurately calibrated, so that no matter what part of the sky we were looking at, the exposure was exactly the same, the sensitivity was exactly the same, and so on. And so an example of an interesting result from the NVSS is that you can show that the radio sources on the sky are distributed extremely uniformly or isotropically, the same in all directions, partly because they're very far away. So you're seeing the distant universe.
Mm-hmm.
And there are so many sources in the NVSS, and the calibration is so precise, it was possible to show that the radio sources are actually not moving compared with the cosmic microwave background. If they were, you'd see more sources bright in one direction and dim in the other direction.
Right. That's fascinating. Thank you so much, Jim. I'm going to move on to our next guest, but we're going to bring you back for the Q&A because there are definitely some questions that are already coming in that I will be calling on you to answer when we return.
Okay.
So if you turn your camera off, and I'll ask Amy to turn her camera on. Hello, Amy.
Hi, Summer.
So what is your role on VLASS?
Yes, so I am the head of operations for the VLA Sky Survey. So I am in charge of overseeing the production of all the products that we produce for the astronomy community. So that's making sure that the raw data that comes off of the VLA is available in NRAO's data archive. And then we run all of that data through calibration pipelines and imaging pipelines so that we produce calibrated data and images that are made from that calibrated data. And all of those data products are looked at by members of NRAO staff, mostly our data analyst team, of which one is here today as well, Sergio Garza. He's one of our data analysts who is focused on VLA Sky Survey data products. So I sort of oversee that team and make sure that nothing falls through the cracks, such as an image that we forgot to make sure was provided to the astronomy community.
Very cool. So since VLASS started its observations in September 2017, but it's still ongoing, sort of what are the types of data products? Are they sort of like early look, or is there a complete set of that entire first scan of the sky that's already been done and calibrated and released?
That's a great question. There's a different kinds of data products that we're trying to produce. So as Faith explained, one thing we're doing is observing the sky 3 times. So we're producing each of the images for each of the observations of the sky. So that we'll have all 3 sets of each type of data product from each epoch of observation. So one of the main goals of the VLA Sky Survey is to identify transient objects. So, supernovas that go off, and so they're visible in one of the epochs and not another epoch, or jets of quasars. Those are supermassive black holes that are actively growing, and they often have jets that emit in radio. And so there are jets that are detected in one of the epochs and not in another epoch, and then they can be followed up as well. So what we do is we produce one set of images called quick look images. And the purpose of those is to be produced as quickly as possible so that anyone can look at them, and basically, usually the comparison is done by computer, but some people do comparisons by eye of particularly interesting objects. And already we're getting some interesting results out, and by we, I actually mean the radio astronomy community. There are astronomers who aren't associated with NRAO, but are using the data products coming from the VLA Sky Survey to identify interesting sources already. And they do that by comparing the quick look images that we've produced to previous images of the radio sky, mostly FIRST and NVSS, the surveys that the sort of legacy VLA surveys. We've actually finished half of the observations for the VLA Sky Survey already. So that's actually that we've observed the entire sky once and half of the sky twice. So there are also results that have come out by comparing the first and second set of VLA Sky Survey observations to each other. So those are the quick look images, and those are produced quickly using algorithms that are not quite as sophisticated in order that they can be produced quickly. But then for other types of science where it's not just looking for a source that appeared or disappeared, but really doing more detailed study of emission from a galaxy, for example, or from jets of a black hole, we're also then spending a longer time producing more science quality images. So basically higher fidelity images with more sophisticated algorithms that just take a lot longer. So there's those 2 sets of images.
And you sort of just alluded to it there when talking about galaxies, but in addition to transients, what are some other science themes or goals or the power of VLASS? What other fields or aspects of types of objects are of interest?
So really it's anything that emits in the radio at 3 gigahertz. So it's different types of galaxies, and it's different types of jets, and It's objects in our own galaxy, in the Milky Way galaxy, such as certain types of stars that are active, so have some interesting physics going on. So they emit in the radio as well, or supernova remnants in our own galaxy. And actually, I think one of the most powerful legacies of the VLA Sky Survey will just be making this very high resolution radio data available across the entire sky, so that astronomers who actually are experts at, say, optical observations with the Hubble Space Telescope, or infrared observations or X-ray observations, but are not experts in radio observations, they will be able to use the radio data to study their own objects. So an interesting thing about astronomy is that the type of observing is necessarily very different across the different frequency ranges. And so sometimes if you need to be an expert in order to figure out what to do with, say, the X-ray data that you've observed, or the infrared data that you've observed. So as a service to the community, to the entire astronomy community and the public, the NRA was doing this radio survey and then making the data products available so that they can be used for science without a lot of work on the part of the scientist who wants to use the data.
Right. I'm glad you brought up other different types of light, because in addition to just having emission that might look different, like the morphology of an object might look different with different types of light, because it's telling you about different phenomena or different aspects of the behavior. Aren't there also differences in the actual parameters of the object that you can get with optical that you can't get with radio?
Yes, exactly. So the different frequencies of light, or different wavelengths or frequencies, are produced from different physical processes that are going on in the galaxy. And so a big area of research, so actually what I did my own PhD dissertation on was comparing the morphology of objects in radio and optical and infrared, and looking at how certain radio properties correlated with other certain infrared properties, or objects with one type of radio emission might have two different types of infrared emission. So the radio tells us about, as I was mentioning, it's usually thermal emission, or so from very warm dust or very hot dust, or it could be jets from supermassive black holes, or it could tell us about star formation processes. But then if we observe in say the optical, we can actually study what type of galaxy it is. So is it a spiral galaxy? Is it an elliptical galaxy? Is it an irregular galaxy, which is a galaxy that doesn't morphologically fit easily into one of the main categories? And so all of those galaxies have different histories, and so we can learn about them. We learn a lot more about objects when we study them and in multiple frequency regimes, and not just in the radio or just in the optical.
Yeah, I always like an example that I learned from one of my advisors, that he kind of likened it to a symphony, and where if you go to the symphony but you only hear the violins, you have no idea the full scope of the music that's being produced. And so you have to look with all these different types of light to get the full story of what's happening in that part of the sky.
Yeah, I guess a really important one is that optical data is usually necessary to figure out how far away an object is. So we can study things in the radio that we know a lot about them, but we actually don't know if they're very bright and close by, or sorry, very bright and really far away, or if they happen to be faint and close by, because those objects can look pretty similar in the radio. And so we need to bring on board optical observations, for example, to tell us if it's an object that's just in our neighboring galaxy, or if it's we're seeing it from across the universe, basically.
That's such a great point. Yeah, once upon a time when I did research, I used NVSS at first to get the radio morphologies and brightnesses, but then I correlated it with the Sloan Digital Sky Survey in order to get what that actual distance to those objects was, so that I could cut out my little cube of the sky and study those objects. Wonderful, Amy. Thank you so much. I'm going to pop over to Sergio real quick, and then we'll bring you back for the Q&A. Sergio, would you like to join us?
Hello.
Hi, welcome.
Thank
So
you for inviting me.
thank you so much for taking your Saturday for us. As a data analyst for VLASS, what does your work entail? What role do you play?
I guess it could be quite a bit because of the fact that we help out with everything from the very beginning of the observation all the way to the actual calibration and imaging and putting it out there. So like we can go anywhere from helping setting up the observations, and we can also double check all the scientists' work to make sure nothing passed through, or let's say a machine somewhere messed up, and then all of a sudden we're up trying to observe a piece of the sky, and then there's a planet right in between us and that, and we have to help figure that out. So there's lots of different things we have to take into account. Another thing is that, like Amy had said, that we have to do a lot of calibration. And with calibration, you have to think about it like we have 27 different radio telescopes at different locations, all recording at different times. It's coming from there all the way to this other spot over here. They have different altitudes, temperatures. They have different like amounts of air and clouds, and like if somebody's driving nearby with the FM radio, we can hear it, we can see it, and it messes up with data. So we have to take into account all the different stuff. So that's what we really mean by calibration. We have to make sure put all of the data that we're doing and putting it on an equal footing, so that we actually see what we're doing, because we're making all 27 telescopes into one really big telescope.
Right.
So there's a lot that can go into that. And on top of that, once you start going into it further, you can also do like sometimes it's harder to see certain things, like when you finally get an image out and then all of a sudden you see like a big blurb somewhere, you don't know what it could be. And it's easier to tell from the imaging than you can just from the data sometimes. And so then you can go back and say, oh, okay, there's this little spot right here that messed up. So let's take that out. Much better picture.
Yeah, that's such a good point. I remember the way that in radio astronomy, the way that you actually look at the data before you turn it into an image, it's not always clear what's really a source and what's a source of interference. And that is sometimes it's easier to go all the way to the imaging state before you can recognize that.
Yeah.
I'm glad you mentioned the people driving by with their FM radios, because the operators often like to talk about how the huge source of interference that Sirius FM satellite is whenever it goes over the VLA.
Yeah, if you ever go by, you can always hear them complaining about it.
What's your favorite part of being a data analyst?
So that's hard to say, but I think there's the instant gratification of being able to go through and like you go through a piece of the sky and you're able to go through it, calibrate, and be able to say like, oh, okay, this is what this actually looks like in the radio. So that's the more instant gratification. The more bigger gratification out of that, the overarching theme is more or less that you're doing work that other people will use for many, many years to come. And so you could go through and like we go through hundreds and hundreds or thousands of images, and sometimes it's not easy to see that there was something really interesting to find in that image. And we're just trying to go through making sure it's good enough for everyone else to see right now. And it's really interesting to think about that somebody could see something I worked on and find something much deeper and much more interesting, or finding a discovery that's way more interesting than we could have ever thought that could have even been asked.
That is really exciting. I look forward to what those might turn out to be, especially once we've completed our third epoch. Fantastic. So you stay where you are.
Okay.
And if Amy and Jim and Faith could all turn their videos and mics back on, we can start addressing some of the Q&A. And one question I just really thought would be fun to ask. I wanted to let Jim know that there's a lot of interest and excitement over your radios and all of the equipment behind you. And so there's a question about, do you have a ham radio call sign?
Yes, I do. I'm AD4YM, and the radios you see behind me are actually old vacuum tube ham radios, which I restore as a hobby. So most of those radios are 40 or 50 or even 60 years old, but they work.
That's amazing. So someone definitely thought that having that many antennas to use must be a dream for you.
Well, if I could actually get to use them for that purpose, it would be interesting. And I've known hams that have made use of radio telescope antennas to contact other hams via moonbound signals. That would be the most obvious use of them.
Has that been done with any of the more, I guess, public larger observatories, or is that more when an amateur builds their own radio dish?
Well, a lot of amateurs build their own, but some of the telescopes in Green Bank have been used to contact other amateurs.
Very cool. Faith.
So Summer, speaking of people noticing things on camera, you had someone compliment your lovely necklace and ask if it was based on an actual observation as well.
It is. It's the jet from M82, the Messier 82 galaxy. So again, it's a contour map that's been turned into color scale.
Great. All
Thanks.
right, so we've been getting a lot of awesome questions here. Thank you everybody for sending those in. We've been answering some of them in the Q&A feature, but for ones that have been flagged to answer live. So one question from Henry is, how can I tell if today's recorded object is different or the same from seeing that same object 6 years from now?
In general, the sky is pretty stable, so that if you see a radio source today, it's very much likely to be there tomorrow. And it depends a little bit on the frequency of observations. So for example, the early VLA Sky Surveys, NVSS and FIRST, were made at 1.4 gigahertz because that's the frequency range at which the sky changes the least, and the surveys then give an archive of what the sky is like that will be valid for many years to come. In contrast to the VLA Sky Survey that was done at 3 gigahertz, where the sky is more variable, and one of the main goals of that survey is to see sources that come and go. Usually it's the same source, but at different levels of activity.
Great. Okay, another question we have here. If you could pick the one biggest discovery and or surprise over the years, what would it be?
That's a free for all. Anyone?
Well, the biggest discovery in astronomy and radio astronomy in general, of course, was the discovery of the microwave background in 1965 that demonstrated that we live in the Big Bang universe. And it certainly qualifies as the most important discovery in the 20th century.
Yeah.
It was completely unanticipated by the people who discovered it. It was an accidental discovery.
Those are always the best too, when someone else validates it. And it was very exciting to have that news come out when that was not even what they thought they were looking for originally.
I've always enjoyed the story about how they got discovered. Just that it was completely by accident, and they didn't know if it was real or if it was instrumental, and they kept observing everywhere. They shoot out birds from the telescope to make sure it wasn't that. They cleaned it out to make sure there was no dirt or poop or nests or anything. They did everything they could to get rid of the noise, and it never went away.
Because it was everywhere. I've got a bit more of a technical question, probably for Amy and Sergio. And you've kind of touched upon this a little bit, because VLASS might be a special case, but someone is asking about the resources we have here. Do we do the data crunching for the researchers, or do the researchers do their own data crunching? And for the latter, how do we actually get the data to the researchers? Like what scale, what magnitude of file size kind of are we talking about?
Okay. A bit of a complicated answer, actually. So most of the the intensive data crunching that needs to be done is the calibration and then the imaging. And that is something that NRAO is doing for the community. After producing images, users are free to then use those images as they like, or even they can download the calibrated data and make images themselves. I don't know if anyone has done that yet, because like I said, it's a very resource intensive algorithms are needed in order to produce images from the VLA Sky Survey because of the way that we're observing the sky and how much data we're producing. So a user might then take images and compare them to other images in the radio or in the optical, and that would be something that they do themselves. Did I answer all of the questions? Oh, and what data sizes? Oh, okay. Let's see. I think I have to actually calculate it on paper, but I think for the VLA Sky Survey in particular, I think 4 hours of observing produces on the order of 0.5 terabyte of raw data. And then that actually increases in size when we do the calibration. And then when we produce the images, then of course the images themselves are quite small. So there's a lot of storage space needed for the intermediate data products. So yeah, if you want to multiply, we're observing for almost 6,000 hours, and then every 4 hours it's 0.5 terabyte of data.
Right. And for a given a non-VLASS observation, do we do like an FTP server or something?
Oh, how does the data get to the community? There is an archive that is accessible via a web browser. And so users can they can select the data there, and normally they choose to download it over the internet. However, they can also, depending on how quickly they need it and how much data they need, it's also possible for us to put it on disk and ship it to people. But sometimes it's either they don't have the storage space, or they don't have the internet, or they don't have the computing resources in order to do the analysis. So NRAO actually has a dedicated cluster of very powerful computers that we allow our users to access. So they can actually just get the data there very quickly, because it's quick to move it from the archive to NRAO's own computers, as opposed to someone downloading it over their home internet. And then they can do the very data intensive and resource intensive parts of analysis on our machines to produce images. And then of course the images are small, and they could then download them to their own machines.
That's pretty cool of us.
Yeah, I think so.
Do you have one, Faith?
Yeah, and I know we're nearing the end of time here, but there are a couple.
Okay, we can do a couple more, I think.
Yeah, so thanks, Stan, for the previous question. This one's from Santiago. How are possible errors during the observations managed? Like, are they corrected on happening, or at the end of the observation, do you ponder them to see if it's been made again? Just like potential observation errors.
So I'm going to jump in and say that most errors are found after the fact, but there are certain types that can be identified during observing. So for example, as was described, the antennas are very large and they're very heavy, and they're moving around in the sky, and we need very, very precise basically, we need them to be pointing just exactly where we want them, because our field of view is very, very tiny on the sky. And so actually there are what's called pointing corrections that are done during the observations themselves. So the antennas will look at a known source that's very bright, and they'll basically do a short scan over it in a square, and figure out how incorrect the pointing is, and then they can actually do a correction during the observations to make sure that they're pointing as close as possible to where we think they're actually pointing. There are operators who keep an eye on issues related to weather, such as wind or rain, and so they might just know that if the weather got so bad during an observation that the data isn't going to be very useful, then they will put the observation back into the observing queue. But it's other types of errors, such as from interference from satellites and so forth. Those are identified by the users after the fact, and that data basically has to be removed via computer algorithms or even sometimes manually.
Great.
I do have a story about RFI from just this past week, which is that there was a private like civilian, like just a single engine plane that happened to be flying nearby the VLA by one of the arms. And we caught all of the RFI from that one little plane that shouldn't have been there, but he was flying nearby. But thankfully, because of how the engine was and the electronics, we weren't observing in that band of radio. And so thankfully nothing got messed up and there was no actual real RFI. But stuff like that can also happen. And immediately the observers will say, hey, this happened during this. We should watch out for that.
Yeah, it's interesting how many devices now that are making our lives easier are making radio astronomers' lives harder. And one of the things, because we're such a destination for road trips, especially people coming in RVs, sometimes don't even realize that they have a Wi-Fi, or they can't turn off their GPS, or they have a microwave. And so we actually have a sign at the site that says no microwaves, because even the people that work at the site and have to have meals at the site are not allowed to use microwaves because of the RFI that it produces. Do we have time for one more, I think? Do you have a good
Great.
one?
With the VLASS as like with VLASS, what's the most obvious difference that you're seeing between that and the other two, like the first full sky survey that we've done with the upgraded version of the VLA? What's the most obvious difference we're seeing between VLASS results and previous results?
I started typing an answer. Jim, do you want to take that one maybe?
Okay, well, the earlier surveys were really intended to provide a snapshot of what the whole radio sky looks like, and that snapshot should be unchanged over many years. And VLASS, on the other hand, was designed to look primarily for variable radio sources. And as a result, it's at a higher frequency and made with a higher angular resolution, which means lower surface brightness sensitivity. So that if you look at an image of the sky, particularly comparing, say, the NVSS and VLASS, what you find is that the sky looks a lot emptier to VLASS, and what it sees is a very large number of very compact radio sources and doesn't see the extended radio sources. It therefore favors objects like quasars, for example, that are stronger emitters at high frequencies and frequently have a lot of flux in a very tiny area.
Fantastic. I think that's about all the time that we have, because we still just have a couple more housekeeping and wrap up things that we want to share with everyone. But thank you so much to Jim and Amy and Sergio for your time and your expertise today. We really enjoyed having you.
Thank you. Goodbye.
Thank you for having us.
All right, I'm going to share my screen again just to wrap things up here. So bear with me for just a sec. All right, so if you want to learn more about the VLA, we have a lot of cool different features on our website that you can go take a look at. So for one thing, we have our VLA mission control. And so if you go to our public website and click on our explore page, if you go to the mission control, this shows you what the VLA and also one of our other radio telescopes is shown there too, what it's currently looking at and the 2 previous projects that it was observing before the current one. And so where it says current observation, it tells you the name of the proposal, like the project name of whatever is being observed right now. And so you can click on it and learn more about the project that the VLA is currently studying. We also have a webcam where you can see what the antennas themselves are currently doing. And the webcam updates I think it's every 15 seconds. And so you can also still see what's happening even at night. The antennas themselves aren't lit up, but there's enough light that the camera is receiving that you can still even get glimpses of what's going on out there during the nighttime as well. And we have a series of videos, our VLA Explorer. And so these can give you more behind the scenes looks at what is happening at the VLA. So that can show you, the videos talk a little bit about the surrounding areas around the VLA site, and even shows you some behind the scenes looks of things that visitors and even some staff members don't regularly get to do, like what it would be like to climb an antenna or go inside the room of our correlator, the supercomputer that we use to compile the data. So each individual video is pretty short. So if you want to learn more and you like watching videos, that's a good way to do so. And we have an interactive VLASS map. So of the data that we've taken and compiled so far, you can go to this map and just interact with it yourself and learn more about stuff that VLASS has already done, scan the sky, as you can see here in this graphic. So this is a great, if you like to do interactive stuff, this is a great way to learn more about VLASS specifically. And so our next tour is going to be, usually we do them every 4 weeks, but the next one is going to be in 3 weeks on Saturday, August 7th. So this year has been our 40th anniversary of the Very Large Array. And so we'll be celebrating those 40 years of science with the VLA at our next event. And that will also be at 1 p.m. Mountain Daylight Time. So if you're interested, definitely make sure that you catch that as well. And thank you so much for watching, and thank you to our guest speakers again for being here. If you are able to, please stick around after the Zoom webinar has closed. There will be a short survey that will pop up. And so if you're willing and able to fill that out, your feedback is really helpful for us to continue to improve these events for the future. So thanks again, everybody, for being here, and hope you have a great rest of your weekend.
Thanks, Faith, and thanks for everybody for joining us. We hope to see you in 3 weeks.